Hello and welcome back to our webcast series on the topic of solids in contact. In this video we're going to look at how to locate the smallest possible solid between two existing solids. Now in our previous videos we were looking at how to locate, say, a new solid when given certain conditions. So the idea of the smallest possible solid is just a different type of condition. So we're going to take an example, and through that example we're going to work out how do we know if we're dealing with the smallest possible solid on our sheets. So we're going to begin by just looking at the question in hand, and we're going to go through the question and just highlight what the conditions that we need to do for it. So it's always a good idea to really clearly read the question first of all and just underline what the actual conditions are. So shown is the elevation and plan of two spheres A and B resting on the horizontal plane. And the question is to draw the plan and elevation of the two spheres and show the projections of the smallest sphere which rests on the horizontal plane and touches both sphere A and sphere B. And we're asked to also show the points of contact in all views. So just highlighting the conditions that we need to be able to solve in order for our question to be correct. You can see the first of them is the smallest possible sphere. So that's our first condition, and then it also has to rest on the horizontal plane. So that's our XY line in elevation, our ground line to you and me, and it also has to touch both sphere A and sphere B. So it has to be in contact with both of those. So there are conditions that we have to meet, and we can tell a little bit about how we're going to solve the question from just reading the question here. From reading the question, I know that I don't know the size of the sphere that we have to put in. So if we don't know the size or the radius of the sphere or the solid that we're going to put in, that means that more than likely we're going to have to use loci to solve our question. So that means we're going to have to take a series of samples in order to solve our question. So if we have to use loci, we're also going to need some way to check to make sure that our answer is correct, or that our locus is giving us the correct size. So in this question here, the thing that we're going to have to check it is the fact that it has to be the smallest possible sphere. So that's the question itself just highlighted. We're going to go and just look and kind of analyze what does this mean to be the smallest possible sphere. So we're going to start off by just looking at a little video. Here we can see we have the setup of our solids. So there's our sphere A, there's our sphere B, and we're going to just imagine a sphere, a third sphere, resting up against the two of them. Now this blue sphere here meets most of the conditions that are set out. You can see from our elevation it's resting on the horizontal plane, our ground line, and you can see from our plan view that it's touching off of sphere A and sphere B. So it's meeting 3 out of the 4 conditions. The fourth condition being that it has to be the smallest possible sphere. So if you can imagine taking this sphere here and just shrinking him down, he still has to touch off the 2 other solids, and he still has to touch off the horizontal plane, but we're going to just see how is he going to move as he shrinks down. You can see as he shrinks, he's getting smaller and smaller as he moves in towards this gap between the 2 solids. Now you can see as he moves down, he gets smaller and smaller and smaller, and at some point he's going to start moving out past the gap, and he's going to start getting bigger and bigger and bigger. So if you actually look at it, if we take the center of each of the 2 solids, well, when he's through the narrowest part of the gap, he's going to be along a line between the 2 of them. So all 3 centers are located along this line at the moment. So that's how we know if we're dealing with the smallest possible sphere. It has to be located on this line here. So the center of our sphere has to be located along that. Now there's 2 ways that we can solve this question. One is by literally taking a series of samples of our sphere as it's getting smaller and smaller, and we're going to discuss that method in the next video. But for this video we're going to just concentrate on our sphere when it's resting in along this line here. You can see if our 3 spheres are resting along this line here, if we were to look straight in here, we would see all 3 solids lined up side by side by side. And side by side by side means that the extreme generators of each of our spheres are going to be seen edge on edge. So we don't have to start off with our solid around the side of the object and maybe roll it around into position. If we could look at our object straight in that direction there, we'd see them all side by side. And we can see that in just this little next clip here. So here we can see there's the 3 solids, and there is our plane just cutting through the middle of them all. So the approach that we're going to take is, first of all, look at them all straight in like that, and we're going to create two loci to locate our sphere in our position here. So you can see all three of them appear side by side when we look in that direction, edge on edge. So we'll see the points of contact where each of the solids touch off each other. So the approach we're going to take is we're going to take a number of samples. So here we can see one sphere touching off sphere A and the horizontal plane. This one here touching off sphere B and the horizontal plane. I'm going to take a number of samples of those, getting bigger until eventually we locate the correct one. So that's the plan of action for what we're going to do. So we're going to look back over here at our question, and the first thing we're going to do is we're going to join up the two centers. So we know this is the line that we have to look along in order to see our solids side by side. So looking in that direction, so looking in perpendicular, if you remember, is the graphical way to say is straight in at. So looking in perpendicular, we create an x1, y1 line parallel with the line from center to center, and we just project on our solids. So the height's been taken from elevation, so the object is still resting on the ground. So there's our first solid, like so. We do the same with the second solid, again taking our height from our elevation, and there's our second solid. Now from our video we could see that we were taking a number of samples, so the size of the samples doesn't really matter initially. We're going to say maybe move up in maybe 5 mil increments. So we're going to start off by drawing our line. This line here represents a sphere of 5 millimeters rolling along the horizontal plane. So as long as it's on this line here, it's going to be on the horizontal plane. We're going to swing an arc then 5 millimeters out from our sphere B, so that guarantees that it's going to be in contact with sphere B. And we're just going to repeat that process for various heights, so getting slightly bigger as we go along. So slightly bigger again off the horizontal plane, off the sphere B, and that's going to give us our locus then. And that locus represents every possible position that our sphere can be in as long as he's touching off the horizontal plane and sphere B. So there are two conditions that we have. We're going to do the same thing again for the horizontal plane and touching off sphere A in this case. So we're going to take our 5 millimeters, our 10 millimeters, our 15, 20, 25, and we can see we're going to get our locus this time for a sphere touching off the horizontal plane and sphere A. So where the two cross must be the solution to our question, insofar as that this point here is the only point that is guaranteeing that we're going to have contact with sphere A, sphere B, and the horizontal plane. Every point on this only meets two of the conditions, every point on this only meets two conditions, but where they cross means three of the conditions. And the fact that it's in this auxiliary here, which we take in by looking in straight in at the narrowest gap, means that this is guaranteed to be the smallest possible sphere. So that's going to be our fourth condition. So there's our center point located. The distance between our center point and the ground is going to give us the radius, and to locate our points of contact we simply join up the centers, giving us the points of contact. Now because we took this view by looking straight in at this line here, we're going to project each of our lines back onto that line. So that's going to locate the position in our plan view. So that's exactly what we do. That's our center point located. There's our solid. Don't forget to put in your hidden detail, because there'll be an overlap one between the other one. And that's a common mistake students make actually, is that they try and fit it so that the three appear edge on edge in the plan view. There will be an overlap because this is much smaller than the two other solids, so you must show that overlap. So we're going to do the same thing then with our points of contact. So there's point of contact 2, point of contact 1, and that's pretty much the plan view of our object finished. So we need then to bring them up into our elevation, straight up, and because our sphere is on the horizontal plane, we're able to just come straight up the radius, giving us our center point, and there it is drawn in. Again, you'll note our hidden detail. And lastly, we need to just join center to center, and from our plan view project straight up to locate our point of contact in our front elevation. So here we have a sphere that meets all the conditions that we need. It's resting on the horizontal plane, it's touching off sphere A, sphere B, and it's the smallest possible sphere. So because it's along this line here, center to center, we know that it's going to be the smallest possible sphere. So like we were saying before, our next video looks through an alternative answer for this question, but I think this way of answering is probably the most direct. It's definitely the least amount of construction for it. So as always, I hope this has been of some use to you, and stay tuned for more videos. Thank you very much.